Alright guys, for this video make sure you have your notebook out, open your data booklet, turn to page 6. We're in topic 4.3, intensity and polarization. So let's define these equations, shall we? This first relationship states that the intensity of a wave, and we are typically dealing with electromagnetic waves, intensity is proportional to this weird looking symbol is proportional to, intensity is proportional to the amplitude of the wave squared. It's not area, it's amplitude. The second equation states that intensity is proportional to the distance you are from the source of the, 1 over the distance you are from the source of the waves squared. So intensity is proportional to 1 over the distance you are from the source of those waves squared. This is an inverse square proportionality. And then this equation is Malice's law. This is the equation, Malice's law. And this equation deals with the relationship between intensity and polarizers. So you have the resulting intensity is equal to the initial intensity times cosine squared of theta, where theta is the angle between two polarizers. And more on this as we proceed with the video. So let's discuss amplitude and intensity. Intensity is the rate energy is being transmitted per area, and it's measured in units of watts, that's power, per meter squared. So remember, power is a rate of energy. This gives us the equation intensity equals power per area. So when we're talking about area, what we mean is like a spherical wave. So imagine the sun, and the sun is emitting light, and as it's sending this light out, it makes, you could imagine that the light comes out of the sun in sort of a large spherical pattern. So we're talking about the surface area of a sphere here. So the area of that of a sphere is 4 pi r squared. In this case, it's 4 pi x squared, where x is the distance you are from the source of the waves. We can rewrite this intensity formula then to be I equals power divided by the equation for the surface area of a sphere, 4 pi x squared, which gives us the fact that intensity is proportional to 1 over x squared. X to the negative 2 power is 1 over x squared. And the total energy of a simple harmonic oscillator like a pendulum is the maximum kinetic energy. Then power must be proportional to the amplitude squared. So this becomes true then, intensity is proportional to amplitude squared. So let's talk about polarization, how polarization affects intensity. Now you can only polarize transverse waves, and the polarization we're going to talk about is just plane polarization or linear polarization. We don't go into circular or elliptical polarization. So light is just random orientations of electric and magnetic fields. What we are concerned with here is the electric field component of light. It's the electric field in light that actually gets polarized. That's what you see in a beam of light. So a beam of light, unpolarized, it has all of these E-field oscillations going in all random directions as represented by these arrows here. And I'm just simplifying this down to just one cross section of this beam. So you can imagine waves oscillating in all directions from a single point. What happens with the polarizer is it absorbs any of these oscillations that aren't oriented in a certain line. So again, any portion of the E field that isn't oriented in line with the polarizer gets absorbed. So when light passes through a polarizer, it is said to be polarized. Go figure. Well, what you can do is you can analyze light if you have more than one polarizer. So let's say we have two polarizers and we place them in front of each other. And then we illuminate these polarizers with a beam of light. We have two filters. There's the first filter, here's the second filter. And if the two polarizers are in line with each other, you will see some light. Light will pass through the two polarizers. But if you rotate one of the polarizers by 90 degrees, what you see is the light is blocked. Light cannot pass through. And you can test this for yourself. If you have polarized sunglasses, hold them up to your computer screen and you should be able to see that the intensity of light is decreased. That's what sunglasses do. But your computer screen has light polarized, or your cell phone screen emits light that's polarized. That light comes out of your screen in one direction. So try now rotating your sunglasses 90 degrees and you should see that the intensity of the light passing through your sunglasses goes to zero. It dims significantly. So in that sense, your computer screen is acting as one polarizer, emitting light with E fields oscillating in only one direction, and your polarized sunglasses act as the second polarizer. In this case, you can definitely reduce the intensity of light down to almost zero. So when you have a series of polarizers, the first filter, the first polarizing filter is called the polarizer. The second is called the analyzer, but they're the same thing. The analyzer is typically the one you rotate. So in this slide, I'm just going to give you some basic trig on Malice's law. And I will show you, here's a beam of unpolarized light, bright yellow. As soon as this beam passes through the first polarizer, its intensity falls by half. It cancels out all of the orientations that aren't in the same direction. So immediately the intensity falls by half as it passes through just a single polarizer. That's why your polarized sunglasses dim light. Now we put a second polarizer up here next to the first polarizer. And if we rotate this second polarizer through to 90 degrees, the two polarizers are perpendicular, no light passes through, intensity falls to zero. Theta is the angle, the angle between the orientation of the first polarizer and the second polarizer, which is known as the analyzer. And here's just a little depiction of the electric field of polarized light from the first polarizer getting passed through, and then incident on the second polarizer, aka the analyzer. And it's only the parallel component, the component of the E field that's in the same direction as the second polarizer that's allowed to pass. So if all of that trig was confusing, worry not, because you're not responsible for being able to reproduce these triangles, but you are responsible for applying Malice's law. Again, I is equal to I naught cosine squared theta, where I naught is the original intensity of the light, and theta is the angle of the analyzer. This results in light of intensity I. Okay, before we do our practice problems, you should know that when light reflects off of a surface, it can be polarized, either fully polarized or partially polarized. And this polarization occurs in the direction parallel to the reflecting surface. And it usually occurs because you have two different media. So for example, air to water or air on concrete. So you have unpolarized light, part of which refracts through this liquid surface. We will talk about refraction soon. And the rest of it gets reflected. And notice that this reflected light is partially polarized. It's mostly oscillating in this horizontal direction, though there is some component that's still oscillating vertically. That's partial polarization. It is why sunglasses tend to be polarized vertically, because light reflecting off of a horizontal road or a lake is mostly oscillating in the horizontal direction. So if you have sunglasses that are polarized in the vertical direction, they block that horizontal light.
Practice 1. A point source emits sound waves of amplitude A. The sound intensity at a distance d from the source is I. What is the sound intensity at a distance 0.5 d from the source when the source emits waves of amplitude 2A? So we have this relationship, and the proportionality symbols means that we can actually build an equation with it. I is proportional to amplitude squared and inversely proportional from the distance squared. So in this case, they don't use x, they use distance d squared. So let's see how the intensity changes with the waves of amplitude 2a, so 2 times the original amplitude, and these need to be squared, divided by d over 2, and that also needs to be squared. So this becomes 4a squared divided by d squared over 4. This 4 comes all the way to the top. So this looks like 16, 4 times 4 is 16, a squared over d squared. This looks like the original equation just multiplied by 16. So our new intensity is 16 times the original. The power emitted as electromagnetic radiation by the sun is approximately 4e26 watts. The radius of the orbit of Mars around the sun is approximately 2e11 meters. What is the best estimate for the power incident on an area of 1 square meter at the radius of Mars's orbit? So here we have the sun on the right-hand side. The sun is emitting radiation, and out here at some distance, 2e11 meters away, is Mars. Now the sun is radiating like a sphere of energy all around it, just coming out and around the sun. So I need to first figure out what is the intensity of light of the power emitted by the sun right here, 2e11 meters away. So intensity equals power divided by this area. The area in this case is the shell or the surface area of this power sphere. So the power of the sun, 4e26 watts divided by a surface area of a sphere. And again, this sphere is the sphere of radiation that's being emitted from the sun. So surface area of a sphere is 4 pi r squared. In this case, my r is the radius I guess it should be from the surface. From the surface of the sun, and that's 2e11 meters. So I'll open parentheses down here. Make sure if you have anything in the denominator, you always put parentheses around everything in the denominator. So 2e11 squared. And here you'll have the intensity of Mars once you calculate that. Now, to find out what is the power incident on 1 meter squared at the radius of Mars's orbit, power now is equal to the intensity times the area. Well, I have the area. It's 1 square meter. That's what they told us from the problem. And so I can get the power that I'm looking for by multiplying the intensity of the light at Mars with the 1 square meter provided. And this will tell me the power at that specific place. 2 wave pulses travel along a string towards each other. The diagram shows their positions at a moment in time. Draw a diagram depicting their superposition a short time later. Superposition meaning what they look like when they overlap. One displacement is positive, one displacement is negative. Use your best judgment and decide what the two will look like when they're totally overlapped.
Practice number 4. The preferred directions of 2 sheets of Polaroid are initially parallel. The second polarizer is rotated such that the amplitude of the transmitted light is reduced by 1/2 Calculate the effect this rotation has on the intensity. Intensity is proportional to amplitude squared. So what happens to this equation, this proportionality, if we change amplitude? Well, let's say that intensity, if we half the amplitude, we still need to square it. We're going to square the half and we square the amplitude. This becomes a squared over 4. Intensity is still proportional to a squared, so for this proportionality to make sense, that means that the intensity has been reduced by a fourth. And you can see that this proportionality is consistent with the one in the data booklet. I'm trying to draw an arrowhead, goodness. So in this case, intensity is reduced by a fourth. All right, it says part B, calculate the angle through which the second polarizer needs to be turned in order to reduce the intensity of the light incident on it by a fourth. So we have this light and it is shining in all directions, unpolarized. It's going through this first polarizer, and then it's going to be incident on a second polarizer. This is the analyzer. And what we want to do is whatever this original intensity is, when it passes through, we want to reduce this intensity by a fourth. So now we're going to take this original intensity that's incident on the second polarizer, aka the analyzer, and we'll reduce it by a fourth. So this requires us to use Malice's law. Intensity transmitted is equal to the original intensity I naught times cosine squared theta, where theta is the angle between the two polarizers. I'm going to replace this I with I naught over 4 because we're trying to reduce that intensity. Incident on polarizer 2 by a fourth is equal to I naught times, and I'm going to rewrite this cosine squared theta as open parentheses cosine theta close parentheses squared. This is how you'll actually write it in the calculator. Type in the calculator to calculate. It means the same thing as cosine squared theta, but you'll see there's no function in your calculator for that, so you just open parentheses cosine theta close parentheses squared. My I naughts cancel, and so this equation becomes 1/4 is equal to open parentheses, cosine theta squared. Take the square root on both sides, and we only deal with the positive solution. This is 1/2 equals cosine theta. Now we want to get the angle theta. So if you remember from trig or your IB math class, you are going to do inverse cosine to get the angle out of this. So you'll see, look at your calculator and click second cos. Doing that gives you cosine to the -1. That's the inverse cosine function. So I'm going to continue up here, theta is equal to cosine inverse, that's second cosine, of 1/2. You do inverse cos on both sides of this equation. Inverse cos here, got cancels, so this is the result. And if you do this in your calculator, you should be able to get the answer. And make sure your calculator is in degree mode. All right, part C of this question, calculate the rotation angle needed to have the intensity from its original value. It's kind of a trick question, actually. Okay, so let's say I have this unpolarized light. It's going in all directions. I'll just draw a couple of directions here. And it's incident on the first polarizer. When it passes through this first polarizer, that original intensity, this original intensity, it gets reduced by 1/2. just by passing through a single polarizer. It's just statistics. If this can go in an infinite number of directions and then you only allow one direction to pass, it just halves the original intensity. So if it passes through a second polarizer, if that second polarizer is in the same line, it will allow that same amount of light to pass through. So the intensity remains 1/2 the original. So the rotation angle needed to half the intensity from its original value, theta, is 0 degrees. Keep them in line and the intensity stays half of the original intensity. Practice number 5. This question is about polarization, obviously. State what is meant by polarized light. So I want you to look in the cognitive textbook. This is topic 4.3, I believe. And I want you to give me a definition and be sure that your definition includes whether or not it's the E field of light that gets oriented in a particular direction, or is it the B field of light EM radiation that gets oriented. So come up with a good definition in your own words, use the textbook as needed, and type that up.
Polarized light of intensity I0 is incident on an analyzer. The transmission axis of the analyzer makes an angle theta with the direction of the electric field of the light. Calculate the intensity of the light through the analyzer when theta equals 45 degrees. So this is Malice's law. I equals I0 times cosine of 45 degrees squared. So your answer will be in units of I0. So you do cosine 45 degrees, square that, and that's times I0. On the axes below, sketch a graph to show the variation with theta of the intensity of the transmitted light. So we are rotating this analyzer, and initially, when there's 0 degrees of rotation, when the analyzer and polarizer are totally parallel, the intensity of light should be equal to the intensity that is incident. It's diminished as we get to 90 degrees and increases again when the polarizer is inverted.
Okay, question number 6. A beam of unpolarized light is incident on the first of 2 parallel polarizers. The transmission axes of the 2 polarizers are initially parallel. The first polarizer is then rotated about the direction of the incident beam by an angle smaller than 90 degrees. Are there any changes to the intensity of the transmitted light? What about changes to the direction of polarization? So if we are rotating the first polarizer, yes, intensity changes. However, no matter what direction that this light goes in after it leaves the first polarizer, it's now incident on a second polarizer. Rotating this first polarizer doesn't change the fact that only light in a certain direction gets passed through the second one. So rotating the first polarizer does change the intensity, but it's the second polarizer that determines what the direction of polarization is, no matter how we rotate this first polarizer, as long as it's less than 90 degrees. Because if it's 90 degrees, then it blocks the light. The light does not pass. So it's the second polarizer. The second polarizer ultimately determines the direction. Polarizer determines the direction of this plane polarized light. Changing the direction or rotating the first polarizer doesn't affect the outcome because it's the second polarizer that leaves its mark. So no, the polarized the polarized direction is determined by the second polarizer. So this question is a conceptual question designed to see, do you understand that no matter which one you rotate, it changes the intensity no matter what, but it's only the second one that determines what the direction of the light, the direction of the beam of light in the end. So it's only the second one. Only rotating the second one will change the direction of polarization, but rotating either one changes the intensity. So that we have this question again. A beam of unpolarized light is incident on the first of two parallel polarizers. The transmission axes of the two polarizers are initially parallel. This time, though, the second polarizer is rotated about the direction of the incident beam by an angle smaller than 90 degrees. Are there any changes to the intensity of the light? And what about polarization? So changes to the intensity of the light? Yes. No matter which one you rotate, the intensity of the light changes. The intensity of this transmitted beam of light is going to change. If it was oscillating in all directions and now we force everything into one direction, we blocked half the light. Now, what about the polarization? If we are rotating the second polarizer, then yes, the direction of polarization does change. Direction of polarization changes. So by rotating the second one, do we get a change in the direction of polarization? Practice number 8. Unpolarized light of intensity I0 is incident on the first of two polarizing sheets. So we initially have this unpolarized light and it's going in all directions. Again, just imagine I can draw these arrows perfectly representing the electric field oscillating in all directions, and it passes through the first polarizer. Oh, it has intensity I0. It passes through the first polarizer and already its intensity gets halved. So initially the planes of polarizations of the sheets are perpendicular. So if these two, this is my first polarizer, here is my second polarizer. If they're perpendicular to each other, then no light gets through. It asks which sheet must be rotated and by what angle so that the light of intensity I0 over 3 can emerge from the second sheet. So we want light, let me draw this. So we're going to have this light coming out, just pretend like I reduced that intensity. I0 over 3 should be emitted. And which sheet can we rotate? So again, it doesn't matter. They don't ask for a final direction of polarization. If they want a final direction of polarization, then we can only rotate the second polarizer. But in this case, if we only care about the intensity, either sheet can be rotated. So which sheet can be rotated? Either. And now we need to see by what angle so that light of intensity I0 over 3 can emerge from the second sheet. So we start using our Malice's law equation here. The intensity of light incident on the second polarizer currently is I0 over 2. We had unpolarized light I0 passes through the first polarizer. Its intensity is automatically halved. Now this intensity of light is incident on the second polarizer, and it's going to be, the second polarizer needs to be rotated at such an angle with respect to the first polarizer such that the light that gets transmitted is I0 over 3. So I can build my Malice's law equation. I0 over 3, this is my resulting intensity, is equal to the incident intensity, I0 over 2, times cosine of theta squared. I0's cancel. 2 over 3 is equal to cosine theta squared. Solve this, give me the angle.
Light of intensity I0 is incident on a polarizer, that is, a single polarizer. The transmission axis of the polarizer is vertical. The polarizer is rotated by an angle theta about the direction of the incident light. The intensity of the transmitted light is measured for various angles theta. On the axes below, sketch graphs to show the variation of the transmitted intensity I when with theta when the incident light is A, horizontally polarized. So the incident light is polarized horizontally, and it reaches this polarizer. So you can imagine I have light like this coming in, and we're going to be rotating this polarizer. And initially, the polarizer is at 0 degrees, and it's going to rotate through some angle. So in this case, when the polarizer is at 0 degrees, it blocks this light. The polarizer only allows light to pass in this direction. Only the vertical direction can pass when it's initially at 0 degrees. So first, there is no intensity. Okay, then when it's at 90 degrees, when we've rotated the polarizer here, we can allow light to pass through. So we will have the transmission axis allows light of the original intensity to pass, and then again at 180 it goes to 0. So this is inverted compared to before. Now we're going to sketch what the intensity looks like when the light is unpolarized. So we have this beam of light coming in, and unpolarized means it has these components of the electric field that are just in every direction possible. So the light that passes through will just naturally be polarized in whatever direction the polarizer is rotated in, so it doesn't matter. But the thing is, having this unpolarized light passing through a single polarizer reduces, there's a reduction in the intensity by 1/2. It's like wearing sunglasses. Even though you only have this single pair of polarizing sunglasses on your face, the light isn't as bright. And statistically, you will cancel about half of the electromagnetic wave when you allow only one direction of this wave to pass. So all the other parts of the waves get canceled and the intensity falls by 1/2. And that's something you're going to have to remember. So with a single polarizer, polarizing unpolarized incident light, it doesn't matter what angle you rotate it through, but the intensity is always reduced to 1/2, no matter what the angle is. Polarized light is incident upon two polarizers as shown below. When the angle between the polarizer and the analyzer is 45 degrees, should the ratio of I over I naught be greater than 0.5, equal to 0.5, or less than 0.5? Well, to determine this, I need to realize that this is like having 3 polarizers in series. I have polarized light incident on this polarizer. Now, this polarized light is coming in at an angle of 0 degrees. This polarizer P is rotated 45 degrees. This polarizer A is rotated 90 degrees. So the angle between these two, the first lights, this is 45 degree difference, 45 degrees, and then 45 to 90 degree rotation because the transmission axis is labeled here with these dashed lines. So from 45 to 90 degrees, this is a rotation angle of 45 degrees. So I'm going to set up 2 Malice's law equations. The first, I'm going to call the light that is emitted out of polarizer P, I'll just call this I sub P, because this is the light that's going to go between these two. And then this transmitted light that comes out of polarizer A is just called I, and the incident on polarizer P is called I naught. So my first Malice's law equation looks like this. I sub P equals I naught times cosine 45 degrees, and this is going to be squared. Note the angle isn't squared. It's the entire function that's squared in this case. Okay, when I do that, I get I sub P equals 0.5 times I naught. We have to do this a second time now because I sub P is the light that's incident on the transmitted light intensity I. So I have a second Malice's law equation, and I'm going to change color to note the change. that my transmitted intensity, I, equals I sub p times cosine 45 degrees, and all this is squared. So IP I can replace with 0.5 I naught. I equals 0.5 I naught times cosine 45 degrees, and this will be squared. When you do this operation, it should be very easy then to determine, is this ratio I over I naught greater than 0.5, equal to 0.5, or less than 0.5? Hopefully you found this video helpful. Thanks for watching.